Let us continue nitrogen family. In nitrogen family, we are seeing the topic oxides of nitrogen. In the oxides of nitrogen, first one is called nitrous oxide. Nitrous oxide. This nitrous oxide formula is N2. Nitrous oxide formula is N2. How to prepare this nitrous oxide in the sense? Take ammonium nitrate. Ammonium nitrate. Ammonium nitrate formula NH4NO3. This is heated. It undergoes thermal decomposition. Now remove all the hydrogens as water molecules. So 4 hydrogen atoms are there, therefore 2 water molecules. So 2 oxygens has gone away. 2 oxygens have gone away, therefore remaining 1 oxygen. Remaining 2 nitrogens are there, therefore we will write N2O. N2O is called nitrous oxide. Suppose if we take NH4NO2, NH4NO2 on heating, what happens means if you remove all the hydrogens as water, remaining is N2. N2 you will get. So ammonium nitrite on heating gives N2. Ammonium nitrate on heating gives N2O, we can say. Then we will take hydroxylamine, NH2H, hydroxylamine, then nitrous acid. Hydroxylamine reacting with the nitrous acid to give nitrous oxide. Okay. This N2O is colorless. N2O is colorless gas, neutral oxide. It can undergo thermal decomposition. N2O on thermal decomposition gives N2 and O2. N2O, nitrous oxide on thermal decomposition gives nitrogen and oxygen, we can say. This N2O is used as an anesthetic in dental surgery. It is used as anesthetic substance. In dental surgery, it is used. Then resonance structures of N2O we will see. Resonance structures of N2O. N2O contains 2 nitrogens and 1 oxygen. This nitrogen group number is 5A. Therefore, this valence shell contains 5 electrons. So 5 dots will write. For this nitrogen also 5 dots will write. Oxygen 6 dots will write. It is coming under 6A group. Now we will give the bonds. Bonds we will give. Here triple bond will give. Here dative bond will give. Nitrogen maximum covalence is 4. It can form 3 normal covalent bonds and 1 dative bond. Okay. This dative bond we will write it as a for a normal covalent bond by giving formal charges. Oxygen is accept or -1, nitrogen is donor +1. Okay, like this we have given. Oxygen is having 3 lone pairs. Next, resonance structure we will write. Next resonance structure is this lone pair coming as pi bond is coming as lone pair. So now we can write this nitrogen is having 2 lone pairs, so negative charge, triple bond becomes a double bond. Then double bond O, oxygen is having 2 lone pairs. Nitrogen plus charge persist because for nitrogen here 4 bonds, here also 4 bonds. Therefore, positive charge of nitrogen is persisting. Oxygen is losing the lone pair. Therefore, -1 is vanishing. Therefore, 0 charge. It is N2O resonance structures we can write. Next oxide is a nitric oxide. Next one is a nitric oxide. Its formula is NO. Nitric oxide formula is NO. Its preparation we'll see. We will take nitrite NO2 minus. Then we will take ferrous Fe2 plus and acid H plus. Now nitrite is converting into nitric oxide. Nitrite is converting into nitric oxide. Ferrous is converting into ferric. Ferrous is oxidizing into ferric. Nitrite is reducing to nitric oxide. Then in order to balance oxygen, we will write water molecule and hydrogen will balance. Okay. So it is a preparation of NO. Then in the atmospheric air, nitrogen is present and oxygen is present. During thundering time, nitric oxide is produced. Okay. During lightning time, nitric oxide will be produced because this required nearly 3000 degrees Celsius. It is endothermic process. Though it is burning with oxygen, it is endothermic process. Here delta H is equal to positive. Generally, combustion means the exothermic, but it is endothermic. This process is endothermic. Okay. Then this nitric oxide is colorless gas. It is a neutral oxide. Then nitric oxide structure we will see. Nitric oxide structure we are seeing. This NO will take. This nitrogen group number is 5. Therefore, its valence shell is having 5 electrons. Oxygen group number 6. Therefore, this valence shell is having 6 electrons. Between nitrogen and oxygen, double bond will be present. Now here, unpaired electron is present. Due to unpaired electron, it is paramagnetic. It is existing in gaseous state. Okay. If this unpaired electron involving in this bonding, then we will say this is 3 electron bond, we will say. Now, unpaired electron involves in bonding. Unpaired electron comes for bonding here. Now, we can say unpaired electron. Here, these 2 electrons make a bond. Here, 3 electrons make a bond. Therefore, 3 electron make a bond, odd electron bond. This unpaired electron goes into a bond. Therefore, this bond contains 3 electrons. Due to unpaired electron, this molecule is a paramagnetic, we can say. This molecule is paramagnetic. But in liquid state, this is showing diamagnetism. Why? Why is it so? Why it is showing diamagnetism? We'll see. Now, 1 electron from oxygen goes to nitrogen. Therefore, nitrogen is getting 2 lone pairs now. Oxygen is having 3 lone electrons. Oxygen is losing 1 electron, therefore positive charge. Nitrogen is gaining 1 electron, therefore negative charge. Another NO will take here minus charge, here plus charge. Therefore, here attraction takes place. That means it forms a dimer. This loose dimerization, loose dimers possible. Like this, dimerization is possible in the liquid state. Therefore, it is diamagnetic. In the liquid state, NO exists as like this dimer. Therefore, NO is a diamagnetic in a liquid. This dimer we can write N2O2. Okay, so NO in vapor state is paramagnetic due to presence of unpaired electron or odd electron bond. NO in liquid state diamagnetic because of dimer, that is N2O2. Okay. Next, let us take magnesium. Let us ignite magnesium in the presence of nitric oxide, in the atmosphere of nitric oxide. So, in the atmosphere of nitric oxide, magnesium is ignited. What will happen? Magnesium continuously burning. Okay, sir. Then we will take sulfur. We will keep sulfur in the atmosphere of nitric oxide. Let us ignite the sulfur. Sulfur is not burning completely, is not continuously burning. Sulfur is not continuously burning, but magnesium is continuously burning. Why? Magnesium is burning with oxygen to give magnesium oxide by liberating energy. That liberated energy is enough for decomposing NO into N2 and O2. This O2 takes magnesium for continuous burning. Okay. Sulfur is burning with oxygen to give sulfur dioxide. It is liberating energy. This liberated energy is insufficient for the decomposition of nitric oxide. So nitric oxide is not decomposing. It is not giving oxygen. So sulfur is not getting oxygen for continuous burning. Okay. So magnesium continuously burns in nitric oxide, but sulfur is not continuously burning in nitric oxide because in the magnesium burning with oxygen to give magnesium oxide, it is liberating energy. The liberated energy is enough for decomposing this nitric oxide. Therefore, oxygen is produced. This oxygen is consumed by magnesium. But in this case, the liberated energy by sulfur burning is insufficient for decomposing this nitric oxide. Therefore, nitric oxide is not decomposing here. Next, we will take nitrogen sesquio oxide, N2O3 we will take. Nitrogen sesquio oxide. Its preparation we will see. Now, this we will write it as NO plus NO2. NO plus NO2 gives N2O3. Okay. You split that 2 nitrogens, 1, 1. 3 oxygens, 2 here, 1 here. So, NO plus NO2 gives N2O3, we can say. Now, this NO here, what is the temperature we are providing means 250 Kelvin. Temperature is 250 Kelvin. That means negative degree Celsius. Negative degree Celsius. At negative degree Celsius, NO2 will be in the dimeric form only. NO2 will be in the dimeric form only. Therefore, NO2 will exist in the form of N2O4. NO2 will exist at a high temperature. N2O4 will exist at a low temperature. At room temperature, between them equilibrium will be there. Okay. Therefore, we will write NO2 in the form of N2O4. Then NO will take 250 Kelvin we are providing. So we are getting N2O3, nitrogen sesqui oxide. For balancing, we will keep 2 times NO, 2 times N2O3. Okay. This N2O3 is blue color solid. Blue solid. This is acidic oxide. How do we say it is acidic oxide? Because this with water, we are getting what in the sense HNO2. HNO2 we are getting nitrous acid. Therefore, it is acidic oxide we can say. In the nitrous acid, if you remove water, we will get N2O3. Therefore, N2O3 is anhydride of HNO2. Anhydride means if you remove water from here, you will get N2O3. Therefore, N2O3 we can say as a anhydride of HNO2. Anhydride of HNO2 we can say. Then N2O3 structure we will see. Now, in the N2O3, 2 nitrogen atoms are there. The 2 nitrogen atoms will write. 3 oxygens are there. For this nitrogen, will give 2 oxygen. For this nitrogen, will give 1 oxygen. Nitrogen will make normally 3 normal covalent bonds and 1 dative bond. Okay, oxygen will make double bond. Nitrogen will make 3 normal covalent bonds. Okay, 1 lone pair will be there because this valence shell contains 5 electrons. This is a N2O3 structure we can say. Next we will go for NO2, nitrogen dioxide. We will take nitrogen dioxide. Now, how to get nitrogen dioxide? We'll see. Take any nitrate salt. Take any nitrate salt, any metal nitrate you take. That on heating gives NO2 gas. Any metal nitrate you take, that you strongly heat it, you will get NO2 gas, you will get it. Nitrogen dioxide will get. For example, we are taking lead nitrate salt. This lead nitrate salt is colorless. This on dry heating gives a lead oxide residue, NO2 gas and O2 gas. So whatever the nitrate, any nitrate you take, that on heating, that will give what? Nitrogen dioxide gas. Okay, sir. Now, generally metal nitrates on heating gives metal oxide, NO2, O2. Exception. Silver nitrate on heating gives silver, NO2, O2. Okay. Silver nitrate on heating gives what in the sense? Silver, NO2, O2. We are not getting silver oxide. Silver oxide is unstable, that undergoes thermal decomposition to give silver and oxygen. Then another exception, mercuric nitrate. Mercuric nitrate on heating gives mercury, NO2, O2. Okay. So mercuric nitrate is not giving mercuric oxide because mercuric oxide easily undergoes thermal decomposition to give mercury and oxygen. So general in the sense, metal nitrate on heating gives metal oxide, NO2, O2. Exception is silver nitrate and mercuric nitrate. Silver nitrate gives silver but not silver oxide. It is giving silver oxide, but that silver oxide easily decomposes to give silver. Mercuric nitrate gives mercuric oxide, but that mercuric oxide easily decomposes to give mercury. Okay. Then next exception, NaNO2, NaNO3, sodium nitrite. Sodium nitrate. This on heating gives NaNO2 and O2. Okay, sodium nitrate on heating gives sodium nitrite and oxygen. Similarly, potassium, rubidium, cesium, but not lithium. Lithium is not coming under this category. Lithium comes under this category only. Lithium nitrate comes under this first category only. So sodium, potassium, rubidium, cesium nitrate on heating gives respective nitrite and oxygen. But on strong heating, what happens means this NaNO2 decomposes to give NO2, O2, Na2O. But on strong heating, what happens means this sodium nitrate also gives sodium oxide, NO2 and O2. Okay. Normal heating means nitrate is converting into nitrite for sodium, potassium, rubidium and cesium. Okay, sir. So how to prepare NO2, that we got idea. Now NO2 is a what in the sense reddish brown gas. Reddish brown gas we can say. In the salt analysis, nitrate salt will be given. Nitrate salt on dry heating. Dry heating in the sense, in the test tube take nitrate salt alone and heat it, you will get NO2 gas, that is reddish brown gas. In the salt analysis, another salt also will give reddish brown gas. What is that? Means a bromine. Bromine gas also reddish brown only. Okay, sir. So reddish brown colored gas in the salt analysis means one is NO2 gas, another one is what in the sense of bromine gas we can say. Sorry. So NO2 gas is reddish brown. We said it is acidic oxide. Why it is so? NO2 with water. NO2 with water, what we are getting in the sense HNO2 and HNO3 we are getting. HNO2 and HNO3 we are getting. So NO2 will take 2 times. NO2 with water gives nitrous acid and nitric acid. Nitric acid. Therefore, NO2 is acidic oxide because it is giving acids. Now we will take HNO2 and HNO3. From these two, if you remove water, you will get NO2. Therefore, NO2 is a anhydride of mixed anhydride of nitrous and nitric acids. So NO2 is mixed anhydride of nitrous and nitric acids, we can say. So, then NO2 structure we will see. NO2 structure we are seeing. Nitrogen we are taking, 2 oxygens we will take. Nitrogen is having 5 electrons in its valence shell. Nitrogen is having 5 electrons in its valence shell because group number is 5a. It is making double bond. Here dative bond only possible. Why? Because nitrogen cannot make 4 normal covalent bonds. Nitrogen cannot make 4 normal covalent bonds. It will make 3 normal covalent bonds and 1 dative bond. Okay. Therefore, why nitrogen is not making 4 normal covalent bonds? That will see. Nitrogen electronic configuration is helium 2s2 2p3. So in the nitrogen, only 3 unpaired electrons are there. Therefore, it can make 3 normal covalent bonds. 1 electron pair is there. Using this electron pair, nitrogen can go for dative bonding. Therefore, only here 1 dative bond and 1 double bond. It is NO2. It is angular structure, bent structure. In the central atom nitrogen, 1 lone electron is there. Because of this odd electron, because of this free electron, this NO2 is paramagnetic. This NO2 we can say paramagnetic, we can say. Now NO2 gas is acidic oxide, therefore it can react with the base. NO2 gas is acidic oxide, therefore it can react with the base. Therefore this acid is reacting with the base to give salts. What are the salts in the sense? NaNO2 and NaNO3. Why? Because this with water gives what? HNO2 and HNO3. HNO2 with NaOH gives NaNO2. HNO3 with NaOH gives NaNO3, we can say. Sir. Then we will go for N2O4, dinitrogen tetroxide. Dinitrogen tetroxide. How to prepare dinitrogen tetroxide means take NO2, nitrogen dioxide, cool this nitrogen dioxide, you will get N2O4. Therefore, NO2 goes for dimerization under low temperature and gives what in the sense N2O4 we can say. N2O4 on heating gives NO2. Therefore, this NO2 and N2O4 can go for equilibrium. At high temperature, NO2 will be possible. At low temperature, N2O4 will be possible. At room temperature, both will be in equilibrium. Both NO2 and N2O4 in equilibrium, we can say. Sir, what is the structure of N2O4? That we will see. Now we will take NO2. NO2 structure, we know that is so and so. We will take NO2 2 times. That NO2 we have written 2 times like this. N2O4 in the sense what you have to do means between nitrogen atoms you have to give bond. Because of this bond, nitrogen is not having lone electron, is not having free electron. Therefore, N2O4 is diamagnetic and it is colorless. It is diamagnetic and it is colorless. It is also acidic oxide because it is nothing but NO2. Okay, it is also acidic oxide, we can say. Next, we will go for nitrogen pentoxide. We are going for nitrogen pentoxide. Formula is N2O5. Okay, now we are going for nitrogen pentoxide. What is the formula means N2O5 we can say. How to prepare this N2O5 we will see. We will take nitric acid. To this we will add dehydrating agent phosphorus pentoxide. Phosphorus pentoxide formula is P2O5. We have written in the dimeric form. Okay, this is taken for distillation. we are getting N2O5, P2O5. This P4O10 takes water molecule from nitric acid and becomes metaphosphoric acid, HPO3, metaphosphoric acid. Okay, therefore nitric acid on dehydration gives a N2O5. Here dehydrating agent what we have used in the sense phosphorus pentoxide, that is P4O10 we have used. This N2O5 is acidic oxide, it is colorless. Why it is acidic oxide? This N2O5 with water gives HNO3. N2O5, this N2O5 with water, N2O5 with water gives what in the sense HNO3 we can say, nitric acid HNO3 we can say. Therefore, it is anhydride of HNO3. Since with water it gives acid, therefore we can call this is as acidic oxide we can say. Therefore, N2O5 is called what in the sense acidic oxide. Now, N2O5 in the vapor state, it is covalent molecule. N2O5 in the vapor state is covalent molecule, but N2O5 in the solid state, it is ionic compound. In the solid state we can say ionic compound, we can say N2O5 in vapor state is covalent, N2O5 in solid state is ionic. Why is it so? That we will see. First we will see N2O5 vapor structure. We will see N2O5 will write N2O5 contains 2 nitrogens and 5 oxygens. Give 2 oxygens to each nitrogen. Remaining 1 oxygen give commonly for both. Now we will give the bonding. Oxygen will make double bond. Oxygen will make double bond. Okay. Oxygen will make 2 bonds, either double bond, otherwise 2 single bonds. Okay. Nitrogen can make 3 normal covalent bonds only. Another one is dative bond. In this dative bond, nitrogen is a donor, oxygen is acceptor. It is N2O5 in vapor state. Okay. What about in a solid state? That we will see. In the solid state, what happens means this bond is migrating to oxygen. Therefore, this becomes this nitrogen is losing the bond, therefore getting positive charge. This oxygen is gaining the bond, therefore getting negative charge. Now this part we will write this NO2 plus, we will write nitrogen is getting positive charge because losing the bond, oxygen is getting negative charge because gaining the bond. So you will get like this NO2 plus, NO3 plus, NO3 minus. NO2 plus is called nitronium. NO2 plus is called what in the sense nitronium. NO3 minus is called nitrate. Therefore, NO2 plus NO3 minus is called nitronium nitrate. This is so and so is existing in solid state. Therefore, N2O5 in solid state exists as NO2 plus NO3 minus. Therefore, solid N2O5 is ionic compound. Solid N2O5 we can call it as ionic compound, but vapor N2O5 we can call it as a covalent compound we can call. Then we'll go for oxo acids of nitrogen. Okay, oxo acids of nitrogen will take oxo acids of nitrogen. Oxo acids in the sense in this compound OH group will be there. That OH group will donate H plus. In this compound OH group will be there. That OH group is donating H plus. That we can say. So first one, the first one is called what in the sense hyponitrous acid. First one is called hyponitrous acid. Hyponitrous acid we can say. This formula is what in the sense HNO. Then we will say nitrous acid. Hypo word we will remove. We will say nitrous acid. Nitrous acid, one oxygen you add, you will get HNO2. Then we will say nitric acid. Acid, we will replace by ic. Therefore, nitric acid will get, you add one oxygen, you will get HNO3. Next one is include the prefix per to the nitric. So we are getting per nitric acid, include one oxygen, you are getting HNO4. Okay. So we got so on. So structures we got. Now we will see we will write the structure for this nitric acid HNO3 we will write, nitrogen we will write, and 3 oxygens we will write. It is oxo acid. Therefore, hydrogen should be present in the form of OH group only. Hydrogen should be present in the form of OH. Now, this oxygen will make 2 bonds. Here 1 bond is there, remaining 1 bond with the nitrogen. Oxygen will make 2 bonds. Therefore, double bond here. Nitrogen can make 3 normal covalent bonds and another one is dative bond. Therefore, here dative bond. This is nitric acid. Next, we will see nitrous acid. We will see in the nitrous acid 1 nitrogen and 2 oxygens are there. it is oxo acid. Therefore, hydrogen should be present in the form of OH group. Oxygen will make two bonds. Here one bond is there, another bond. This oxygen makes a double bond. Nitrogen comes under 5A group. Therefore, this valence shell contains 5 electrons. Out of 5 electrons, 3 electrons have gone for bonding. Remaining 2 electrons we have given. Then we'll go for hyponitrous acid. Hyponitrous acid means it is also oxo acid. Therefore, hydrogen present in the form of OH group only. Okay, this oxygen is making bond with nitrogen. Here nitrogen is having only one bond. Therefore, nitrogen is what this species is doing means it is going for dimerization. It is going for dimerization. In the dimerization, what happens means between two nitrogen atoms, a double bond is possible. Now each nitrogen is having one lone pair. Therefore, hyponitrous acid formula is what means H2N2O2. It is dimer, we can say. Next, we will see this pernitric acid. Pernitric acid in the sense here peroxy linkage is present. So, how many oxygens are in peroxy linkage? How to find? For that case, what we have to do means we have to find how many oxygens peroxides that we have to find. So, you give the oxidation number of hydrogen, that is +1. Hydrogen oxidation number we have given. Nitrogen oxidation number, what you have to do means its group number, what you see, its group number is 5A. Therefore, you give its maximum oxidation number +5. Why we have to give maximum oxidation number for nitrogen means in order to find how many oxygens are peroxides. For that case only, to find how many oxygens peroxides and how many oxygens oxides, we have to give the variable oxidation number element as maximum oxidation number. Nitrogen can show variable oxidation numbers. It can start oxidation number from -3 to +5, it can give. Therefore, in this case, we want to find how many oxygens are having peroxides. Therefore, give nitrogen its maximum oxidation number. Maximum oxidation number of nitrogen is 5 because this valence shell contains 5 electrons. Therefore, +5 we have given. Now, X number of oxygens is taking -1. -1 means oxidation number of oxygen in peroxide. How many are having -1 means X number of oxygens. Remaining are oxides. Remaining means 4 minus X. Oxides means oxygen oxidation number is -2. Net charge is equal to 0. Now you find X. X is equal to 2. That means 2 oxygens carry -1. That means 1 peroxide linkage is present. 1 peroxide is present. 1 peroxide means O2 2 minus. Peroxide linkage, how to give, we will see. These 2 oxygens will give. Oxygen group number is 6A. Therefore, oxygen is having 6 electrons in its valence shell. Here also 6 electrons in the valence shell, we can say. And -2 we will give -1 to this oxygen, -1 to this oxygen. So that additional 1 electron we will give here. Between these 2 electrons, a bond is possible. This is called peroxide linkage. This is called peroxide. 1 peroxide ion means formula O2 2 minus. Here X is equal to 2 means 2 oxygens carrying -1. That means in HNO4, 1 peroxide linkage is present, we can say. So now we will give 1 peroxide linkage for this. Okay, HNO4 we have given. And then we have to give hydrogen. We have to give hydrogen, give to peroxide only. Hydrogen give to peroxide. Okay, then this oxygen 2 bonds. So for each oxygen 2 bonds you give it. Now this nitrogen can make 1 dative bond only. This is called pernitric acid, we can say. Okay, this is about oxo acids of nitrogen structures. Next we will go for nitric acid preparation. We'll see. Now we will take about nitric acid, that preparation and chemical properties uses we will see. Now nitric acid preparation we are going for preparation of nitric acid. Now how to prepare this? Laboratory. In the laboratory we will take sodium nitrate, otherwise potassium nitrate we will take. That we will heat with corn sulfuric acid, concentrated sulfuric acid. What we will get in the sense nitric acid we will get HNO3 we will get. Then we will get a salt. Salt is sodium, otherwise potassium bisulfate we will get. Okay, it is a laboratory preparation. Then manufacture of nitric acid we will see by Ostwald method. By Ostwald method, let us manufacture nitric acid. Now, initially what we have to do means we have to take ammonia. We have to take that ammonia is treated with oxygen gas in the presence of catalyst. What is a catalyst means platinum catalyst, otherwise rhodium gas catalyst. Platinum gas, otherwise rhodium gas act as a catalyst. and temperature is 500 Kelvin here, and pressure is 9 bar is given. What we are getting in the sense nitric oxide we are getting and water. Then this nitric oxide burns with oxygen. This nitric oxide burns with oxygen to give what in the sense nitrogen dioxide. This nitrogen dioxide dissolves in water. Nitrogen dioxide dissolves in water to give what in the sense HNO3 and NO. Here this reaction is called disproportionation reaction because here nitrogen is plus 4 is converting into plus 5 here, and here plus 2. So plus 4 into plus 5 oxidation, plus 4 into plus 2 reduction, we can say this is disproportionation reaction. In this method, this method is called Ostwald method. In this Ostwald method, we are preparing what in the sense nitric acid by taking ammonia and oxygen. Let us balance this equation. Here nitrogen 4 times, oxygen 5 times. Here nitric oxide 4 times, water 6 times. It is balanced. Next, let us balance this one. Here 2 2 we will write. We will balance this one. Here 3, here 2. Okay, we have balanced this equation. Now we got aqueous solution of HNO3 we got now. Okay, now we got which solution in the sense aqueous solution of HNO3 we got in this Ostwald process. Then this aqueous solution of nitric acid is taken for distillation. We are getting concentrated nitric acid. We are getting a concentrated nitric acid. This mass percentage, how much in the sense this mass percentage is equal to 68%, we can say. The mass percentage is 68%. This nitric acid only we are using in the laboratory as concentrated nitric acid. In the laboratory we are using concentrated nitric acid, this one only, mass percentage 68% nitric acid we are using. Then if you want to remove still more water, if you want to take still more higher percentage of mass percentage, means take this nitric acid, treat with concentrated sulfuric acid. Corn sulfuric acid takes water molecules from here. Therefore concentration of nitric acid is still raised. Now the mass percentage becomes how much in the sense 98%. Now you see that concentrated sulfuric acid is a better dehydrating agent. It is having high affinity with water. Therefore it takes water molecules from here. Therefore mass percentage of nitric acid is increased to 98%. Okay, so next we will see about commercial nitric acid. The commercial nitric acid, if you see that that will appear yellow color. Even in the laboratory also you can see concentrated nitric acid, you can see that is colorless only. If the concentrated nitric acid is left without usage for 1 year or 2 years, if you leave it, then you see that that corn nitric acid will appear yellow color even in the school lab. Why that corn nitric acid is appearing a yellow color? Because corn nitric acid undergoes photochemical decomposition. Due to photochemical decomposition, it gives NO2 and O2. This NO2 is dissolving in corn nitric acid and gives yellow color to the corn nitric acid. So commercially available corn nitric acid will be yellow color because of presence of dissolved NO2. Okay, so commercial nitric acid, commercial concentrated nitric acid will appear yellow color due to dissolution of what? NO2 in HNO3. Okay, if you leave HNO3, if you leave corn nitric acid for several days, that means 1 year or 2 years, if you leave also, this corn nitric acid will become yellow color because this nitric acid undergoes decomposition in the presence of sunlight to give NO2 and O2. This NO2 dissolves in HNO3 and gives yellow color to this solution. Okay, then we will see chemical properties of this nitric acid. We will see. Now we will take chemical properties. Very dilute nitric acid will take. If we take very dilute nitric acid, this in the presence of very dilute nitric acid, iron is converting into ferrous. Iron is converting into ferrous. Sir, zinc is converting into zinc ion. Zinc is converting into zinc ion in the presence of a very dilute nitric acid. In this case, very dilute nitric acid is converting into what in the sense ammonia. In this case, very dilute nitric acid is converting into what in the sense ammonia. Okay, so very dilute nitric acid is converting into ammonia here. Here also converting into ammonia. Okay, so if you take very dilute nitric acid, iron is converting into ferrous. Ferrous takes nitrate and becomes ferrous nitrate. Zinc is converting into Zn2 plus. Zinc ion takes nitrate and becomes zinc nitrate. While nitric acid becomes ammonia, this ammonia is acid. It will react with HNO3 to become ammonium nitrate. Ammonium nitrate. Okay. Next we will take dilute nitric acid. We'll see. Now we are taking dilute nitric acid. So we are taking dilute nitric acid. Now iron is converting into ferrous with the dilute nitric acid. Zinc is converting into zinc ion with the dilute nitric acid. Copper is converted into cupric ion with the dilute nitric acid. Tin is converted into stannous with the dilute nitric acid. Okay, with the dilute nitric acid, so and so is happening. Okay, when iron is converting into ferrous, dilute nitric acid becomes N2O, nitrous oxide. When zinc becomes zinc ion, dilute nitric acid becomes nitrous oxide N2O. When copper becomes cupric, dilute nitric acid becomes NO, nitric oxide. Dilute nitric acid becomes NO, nitric oxide. When tin becomes stannous, dilute nitric acid becomes ammonia. Dilute nitric acid becomes ammonia. So, now ferrous takes nitrate and becomes ferrous nitrate. Zinc takes nitrate and becomes zinc nitrate. Cupric takes nitrate and becomes cupric nitrate. Stannous takes nitrate and becomes stannous nitrate. N2O is neutral oxide not reacting with HNO3. NO is neutral oxide not reacting with HNO3. Ammonia is a base, so react with this acid to give ammonium nitrate. Then we will see concentrated nitric acid. We will take concentrated nitric acid. What is the reaction now? We will see. Now this iron is oxidizing into ferric, whereas in this case ferrous, here also ferrous. With very dilute nitric acid, iron gives ferrous. With the dilute nitric acid, iron gives ferrous. With the con nitric acid, iron gives ferric, we can say. Iron gives ferric. Sorry. Then zinc gives zinc ion, Zn2 plus only. Zinc can show only +2 oxidation number. It cannot show variable oxidation numbers. Copper gives cupric ion, Cu +2. Tin gives what in the sense +4 oxidation number, stannic. Tin becomes stannic. Here tin becomes stannous. Stannous in dilute nitric acid, stannic in concentrated nitric acid. These are metals. Non-metals, if we take, iodine becomes iodic acid. In iodic acid, iodine is +5 oxidation number. Iodine can show maximum +7 oxidation number. Here +5 it shows. Carbon with con nitric acid gives carbon dioxide. Carbon is having +4 oxidation number. Sulfur gives sulfuric acid. Sulfuric acid with concentrated nitric acid. Phosphorus gives orthophosphoric acid. Orthophosphoric acid. Now here phosphorus is having maximum oxidation number here. Sulfur is having maximum oxidation number here. Carbon is having maximum oxidation number here. Iodine alone is not having maximum oxidation number, that is +7, but it shows +5. In all the cases, nitric acid will become NO2. Concentrated nitric acid means that will convert into nitrogen dioxide in all the cases. Okay. Now ferric takes nitrate and becomes ferric nitrate, zinc nitrate, cupric nitrate. This SN4 plus will exist as metastannic acid. H2SNO3. Metastannic acid, we have to say. Metastannic acid. Metastannic acid. H2SNO3 exists as a metastannic acid, we can say. Okay. Now this con nitric acid, chemical properties so and so. Then we will see how noble metals will react with corn nitric acid. We'll see. Now noble metals will take. Noble metals in the sense, what means gold, platinum, these and all noble metals. Noble metals are not affected by concentrated nitric acid. Noble metals are not affected by corn nitric acid, we are saying. Okay, we'll continue in next class.